Here's the size, transforms, of the original image size over 2. These two slashes in Python means integer divide, okay, because obviously we can't have half pixel amounts in our sizes. So integer divide over 2. And we'll use batch size of 8. That fits on my GPU. It might not fit on yours. If it doesn't, you can just decrease the batch size down to 4. And this isn't really solving the problem, because the problem is to segment all of the pixels, not half of the pixels. So I'm going to use the same trick that I did last time, which is I'm now going to put the size up to the full size of the source images, which means I now have to halve my batch size, otherwise I won't have GPU memory. And I'm then going to set my learner. I can either say learn.data equals many data, or I actually found I had a lot of trouble with GPU memory, so I generally restarted my kernel, came back here, created a new learner, and loaded up the weights that I saved last time. But the key thing here being that this learner now has the same weights that I had here, but the data is now the full image size. So I can now do an LR find again, find an area where it's kind of well before it goes up. So I'm going to use one in X3 and fit some more, and then unfreeze and fit some more, and you can go to learn.show results to see how your predictions compare to the ground truth. And I'm going to say they really look pretty good. Got that, huh? So how good is pretty good? An accuracy of 92.15. The best paper I know of for segmentation was a paper called the 100 Layers Tiramisu, which developed a convolutional dense net, came out about 2 years ago. So after I trained this today, I went back and looked at the paper to find their state-of-the-art accuracy. Here it is. And I looked it up, and their best was 91.5, and we got 92.1. So I gotta say, when this happened today, I was like, wow. I don't know if better results have come out since this paper, but I remember when this paper came out, and it was a really big deal. I was like, wow, this is an exceptionally good segmentation result. When you compare it to the previous bests that they compared to, it's a big step up. And so like in last year's course, we spent a lot of time in the course re-implementing 100 Layers Tiramisu. And now, with our totally default fast AI class, I'm easily beating this. And I also remember this I had to train for hours and hours and hours, whereas today's I trained in minutes. So this is a super strong architecture for segmentation. So yeah, I'm not going to promise that this is the definite state of the art today, because I haven't done a complete literature search to see what's happened in the last 3 years, but it's certainly beating the world's best approach the last time I looked into this, which was in last year's course yesterday. And so these kind of just all the little tricks, I guess, we've picked up along the way in terms of like how to train things well, things like using the pre-trained model, and things like using the one-cycle convergence, and all these little tricks. They work extraordinarily well. And it's really nice to be able to like show something in class where we can say, I've yet to publish the paper on the exact details of how this variation of the UNet works. There's a few little tweaks we do, but if you come back to part 2, we'll be going into all the details about how we make this work so well. But for you, all you have to know at this stage is that you can say learn about your UNet, and you should get great results also. There's another trick you can use if you're running out of memory a lot, which is you can actually do something called mixed precision training. And mixed precision training means that instead of using, for those of you that have done computer science, instead of using single precision floating point numbers, you can do most of the calculations in your model with half precision floating point numbers, so 16 bits instead of 32 bits. The very idea of this has only been around really for the last couple of years in terms of like hardware that actually does this reasonably quickly. And then Fast AI library, I think, is the first and probably the only that makes it actually easy to use this. If you add 2 FP16 on the end of any learner call, you're actually going to get a model that trains in 16-bit precision. Because it's so new, you'll need to have kind of the most recent CUDA drivers and all that stuff for this even to work. I tried it this morning on some of the platforms that just killed the kernel, so you need to make sure you've got the most recent drivers. But if you've got a really recent GPU, like a 2080 Ti, not only will it work, but it'll work about twice as fast as otherwise. Now, the reason I'm mentioning it is that you're going to use less GPU RAM. So even if you don't have like a 2080 Ti, you might find, or you'll probably find, that things that didn't fit into your GPU without this, then do fit in with this. Now, I actually have never seen people use 16-bit precision floating point for segmentation before. Just for a bit of a laugh, I tried it, and actually discovered that I got an even better result. So I only found this morning, so I don't have anything more to add here, other than quite often when you make things a little bit less precise in deep learning, it generalizes a little bit better, and I've never seen a 92.5 accuracy on Canvas before. So yeah, this not only will this be faster, but you'll use bigger batch sizes, but you might even find, like I did, that you get an even better result. So that's a cool little trick. You just need to make sure that every time you create a learner, you add this to FP16. If your kernel dies, it probably means you have slightly out of date CUDA drivers, or maybe even an too old graphics card. I'm not sure exactly which card support FP16. Okay, so one more before we kind of rewind. Sorry, 2 more. The first one I'm going to show you is an interesting data set called the BB Tempos data set. And Gabriel Finale was kind enough to give us permission to use this in class. His team created this cool data set. Here's what the data set looks like. It's pictures. It's actually a few things in that. We're just going to do a simplified version. And one of the things they do is they have a dot saying this is the center of the face. And so we're going to try and create a model that can find the center of the face. So for this data set, there's a few data set specific things we have to do, which I don't really even understand, but I just know from the reading you have to. They use some kind of depth sensing camera. I think they actually use like that.
Okay, hang on. So this doesn't even seem like it's a prediction problem anymore, or like a classification or segmentation problem. It's a different class altogether. I mean, it's kind of like segmentation, where you need to decide on each pixel, on a pixel by pixel basis, what sort of category it falls into. And here we just have a discrete category, which is either center face or not center face. Maybe it's like that. It's like segmentation in that perspective. But let's see what he says.
Connect, Xbox Connect. There's some kind of calibration numbers that provide a little file which I have to read in, and then they provide a little function that you have to use to take their coordinates to change it from this depth sensor calibration thing to end up with actual coordinates. So when you open this and you see these little conversion routines, that's just I'm just doing what they told us to do, basically. It's got nothing particular to do with deep learning to end up with this stuff. The interesting bit really is where we create something that's not an image or an image segment, but an image points. And we'll mainly learn about this later in the course. But basically, image points is this idea of kind of the coordinates, right? They're not pixel values, they're x, y coordinates. There's just two numbers. As you can see, let's see. So here's an example for a particular image file name. This particular image file, here it is. The coordinates of the center of the face are at 263, 428, and here it is. So there's just two numbers, which represent whereabouts in this picture is the center of the face. So if we're going to create a model that can find the center of the face, we need a neural network that spits out two numbers. But no, this is not a classification model. These are not two numbers that you look up in a list to find out that they're road or building or ragdoll cat or whatever. They're actual locations. So, so far, everything we've done has been a classification model. Some of these created labels or classes. This, for the first time, is what we call a regression model. A lot of people think regression means linear regression. It doesn't. Regression just means any kind of model where your output is some continuous number or set of numbers. So this is an integrated image regression model, something that can predict the...
Okay, so that answers the question, right? It's not a classification problem anymore. It's a regression problem. So when the output is continuous, it's considered regression, not discrete. So not like a group that you're picking from, but a continuous output, like a coordinate.
Two numbers. So how do you do that? Same way as always, right? So we can actually just say, I've got a list of image files, it's in a folder, and I want to label them using this function that we wrote that basically does the stuff that the README says to grab the coordinates out of the text files. That's going to give me the two numbers for every one, and then I'm going to split it according to some function. And so in this case, the files they gave us, again, they're from videos, and so I picked just one folder to be my validation set. In other words, a different person. Okay, I was trying to think about, like, how do I validate this fairly? So I said, well, the fair validation would be make sure that it works well on a person that's never seen before. So my validation set is all going to be a particular person. Create a data set, and so this data set, I just tell what kind of data set is it? Well, they're going to be sort of points. The points means specific coordinates. Do some transforms. Again, I have to say transform by equals true because that red dot needs to move if I flip or rotate or walk. Okay? Pick some sizes. The size is going to work pretty quickly. Create a data bunch, normalize it, and again, show batch. There it is. Okay. I noticed that their red dots don't always seem to be quite in the middle of the face. I don't know exactly what their kind of internal algorithm for putting dots on. Kind of sometimes looks like it's going to be a nose, sometimes it's not quite a nose. Anyway, get the it's somewhere around the center of the face or nose. So how do we create a model? We create a CNN. But we're going to be learning a lot about loss functions in the next few lessons. But generally, basically, the loss function is that number that says how good is the model. And so for classification, we use this loss function called cross-entropy loss, which says basically, remember this from earlier lessons, did you predict the correct class, and were you confident with that prediction? Now, we can't use that for regression, so instead we use something called mean squared error. And if you remember from last lesson, we actually implemented mean squared error from scratch. It's just the difference between the two squared and added up together. Okay, so we need to tell it this is not classification, so we use mean squared error. This is not classification, so we have to use mean squared error. And then once we've created the learner, we've told it what loss function to use, we can go ahead and do find. We can then fit, and you can see here, within a minute and a half, our mean squared error is 0.0004. The nice thing is about like mean squared error is very easy to interpret, right? So we're trying to predict something which is somewhere around a few hundred, and we're getting a squared error on average of 0.0004. So we can feel pretty confident that this is a really good model. And then we can look at the results. I learned the results, and you can see predictions, ground truth. It's doing a really perfect job. Okay, so that's how you can do image regression models. So anytime you've got something you're trying to predict, which is some continuous value, you use an approach that's something like this. So, last example before we look at some kind of more foundational theory stuff, NLP. And next week we're going to be looking a lot more NLP. But let's now do the same thing, but rather than creating a classification of pictures, let's try and classify documents. And so we're going to go through this in a lot more detail next week, but let's do a quick version. Rather than importing from FastAI.vision, I now import for the first time from FastAI.text. That's where you'll find all the application-specific stuff for analyzing text documents. And in this case, we're going to use a data set called IMDb, and IMDb has lots of movie reviews. They're generally about a couple of thousand words. And each movie review has been classified as either negative or positive. So this is in CSV files, we can use pandas to read it, we can take a look, we can take a look at a review. And basically, as per usual, we can either use factory methods or the Datablock API to create a data bunch. So here's a quick way to create a data bunch from a CSV of texts, data bunch from CSV, and that's that. And yeah, at this point, I could create a learner and start training it. But I'm going to show you a little bit more detail. We're mainly going to look at next week. The steps that actually happen when you create these data bunches is there's a few steps. The first is it does something called tokenization, which is it takes those words and it converts them into a standard form of tokens. So it's basically each token represents a word, but it does things like see here. See how did has been turned here into two separate words, and you see how everything's been lowercased. See how your has been turned into two separate words. So tokenization is trying to make sure that each token, each thing that we've got with spaces around here represents a single linguistic concept. Okay. Also, it finds words that are really rare, like really rare names and stuff like that, and replaces them with a special token called unknown. So anything starting with XX and FastAI is some special token. So this is tokenization. So we end up with something where we've got a list of tokenized words. We'll also see things like punctuation end up with spaces around them to make sure that they're separate tokens. The next thing we do is we take a complete unique list full of possible tokens. That's called vocab, and that gets created for us. And so here's the first 10 items of the vocab. So here is every possible token, the first 10 of them that appear in all of the movie reviews. And we then replace every movie review with a list of numbers. And the list of numbers simply says what numbered thing in the vocab is in this place. So here's 6. Here's 0, 1, 2, 3, 4, 5, 6.
Okay, so this looks similar to the stuff that we saw earlier with segmentation, where you had building and pedestrian, whatever, road, and each one is just referenced by a number. So this is the same thing.
So this is the word yeah, this is 3, 0, 1, 2, 3, this is a comma, and so forth. Right? So through tokenization and numericalization, this is a standard way in NLP of turning a document into a list of numbers. We can do that with the data block API, right? So this time it's not image files list, it's text with data from a CSV, convert them to data sets, tokenize them, numericalize them, create a data bunch, and at that point, we can start to create a model. As we'll learn about next week, when we do NLP classification, we actually create 2 models. The first model is something called a language model, which, as you can see, we train in a kind of usual way. We say we want to create a language model learner, we train it, we can save it, we unfreeze, we train some more, and then after we've created a language model, we fine-tune it to create a classifier. Here's the thing where we create a data bunch for classifier, we create a learner, we train it, and we end up with some accuracy. So that's the really quick version. We're going to go into it in more detail next week. You can see the basic idea of training an NLP classifier is very, very, very similar to creating every other model we've seen so far. And this accuracy, so the current state of the art for IMDb classification is actually the algorithm that we built and published with a colleague called Sebastian Ruder. And this basically, what I just showed you is pretty much the state of the art algorithm with some minor tweaks. You can get this up to about 95% if you try really hard. So this is very close to the state of the art accuracy that we developed. There's a question. Okay, now's a great time for a question.
For a data set near a different ImageNet, like the satellite images or genomic images shown in Lesson 2, we should use our own stats. Jeremy once said, if you use your pre-trained model, you need to use the same stats it was trained with. Why is that? Isn't it that normalized data with its own stats will have roughly the same distribution like ImageNet? The only thing I can think of which may differ is skewness. Is it the possibility of skewness or something else the reason for statement? And does that mean you don't recommend using pre-trained models with very different data sets, like the 1-point mutation that you mentioned in Lesson 2?
Nope. As you can see, I've used pre-trained models for all of those things. Every time I've used an ImageNet trained pre-trained model, and every time I've used ImageNet stats. Why is that? Because that model was trained with those stats. So, for example, imagine you're trying to classify different types of green frogs. So, if you were to use your own per channel means in your dataset, you would end up converting them to a mean of 0, a standard deviation of 1 for each of your red, green, and blue channels, which means they don't look like green frogs anymore. They now look like red frogs. Right? But ImageNet expects frogs to be green. Okay? So you need to normalize with the same stats that the ImageNet training people normalized with, otherwise the unique characteristics of your dataset won't appear anymore. You actually normalize them out in terms of the per channel statistics. So you should always use the same stats that the model will train with. Okay, so in every case, what we're doing here is we're using gradient descent with mini batches, so stochastic gradient descent, to fit some parameters of the model. And those parameters are parameters to basically matrix multiplications. In the second half of this part, we're actually going to learn about a little tweak called convolutions, but it's basically a type of matrix multiplication. The thing is, though, no amount of matrix multiplications is possibly going to create something that can read IMDb movie reviews and decide whether positive or negative, or look at satellite imagery and decide whether it's got a road note. That's far more than a linear classifier can do. Now, we know these are deep neural networks, and deep neural networks contain lots of these matrix multiplications, but every matrix multiplication is just a linear model. And a linear function on top of a linear function is just another linear function. Right? If you remember back to your high school math, you might remember that if you have a y equals ax plus b, and then you stick another c y plus d on top of that, it's still just another slope and another intercept. So no amount of stacking matrix multiplications is going to help in the slightest. So what are these models actually? What are we actually doing? And here's the interesting thing. All we're actually doing is we literally do have a matrix multiplication or a slight variation like convolution that we'll learn about. But after each one, we do something called a nonlinearity or an activation function. An activation function is something that takes the result of that matrix multiplication and sticks it through some function. And these are some of the functions that we use. In the old days, the most common function that we used to use was basically this shape. These shapes are called sigmoid. And they have particular mathematical definitions. Nowadays, we almost never use those for these between each matrix multiply. Nowadays, we nearly always use this one. It's called a rectified linear unit. It's very important when you're doing deep learning to use big long words that sound impressive. Otherwise, normal people might think they're good too. But just between you and me, the rectified linear unit is defined using the following function. That's it. Okay, so if you want to be really exclusive, of course, you then shorten the long version and you call it ReLU to show that you're really in the exclusive king. So this is a ReLU activation. Right? So here's the crazy thing. If you take your red, green, blue pixel inputs and you chuck them through a matrix multiplication, and then you replace the negatives with 0, and you put through another matrix multiplication, place the negatives with 0, and you keep doing that again and again and again, you have a deep learning neural network. That's it. Right? So how the hell does that work? So an extremely cool guy called Michael Nielsen showed how this works. He has a very nice website, like a modern website called Neural Networks and DeepLearning.com. And he has these beautiful little JavaScript things where you can get to play around, because this was back in the old days, this was back when we used to use sigmoids. Right? And what he shows is that if you have enough he shows these little matrix multiplications. If you have enough little matrix multiplications followed by sigmoids, and exactly the same thing works for a matrix multiplication followed by ReLU, you can actually create arbitrary shapes. Right? And so this idea that these combinations of linear functions and nonlinearities can create arbitrary shapes actually has a name, and this name is the universal approximation theorem. And what it says is that if you have stacks of linear functions and nonlinearities, the thing you end up with can approximate any function arbitrarily closely. So you just need to make sure that you have a big enough matrix to multiply by or enough of them. So if you have, now this function, just a sequence of matrix multiplies and nonlinearities, where the nonlinearity is going to be, basically any of these things, we don't use this one. If that can approximate anything, then all you need is some way to find the particular values of the weight matrices in your matrix multiplies that solve the problem you want to solve. And we already know how to find the values of parameters. We can use gradient descent. And so that's actually it. Right? And this is the bit I find the hardest thing normally to explain to students, is that we're actually done now. People often come up to me after this lesson and they say, what's the rest? Please explain to me the rest of deep learning. But there's no rest. We have a function where we take our input pixels, whatever, we multiply them by some weight matrix, we replace the negatives with zeros, we multiply by another weight matrix, replace the negatives with zeros, do that a few times, we see how close it is to our target, and then we use gradient descent to update our weight matrices using the derivatives, and we do that a few times, and eventually we end up with something that can classify media reviews, or can recognize pictures of ragdoll cats. That's actually it. Okay. So it's the reason it's hard to understand intuitively is because we're talking about weight matrices that have, once you read them all up, something like 100 million parameters. They're very big weight matrices. Right? So your intuition about what multiplying something by a linear model and replacing the negatives with zeros that you can do, your intuition doesn't hold. Right? You just have to accept empirically the truth is doing that works really well. So in part 2 of the course, we're actually going to build these from scratch. Right? But just to skip ahead.
It's like this concept of approximating the tower, or whatever it is, the shape that he showed earlier, with so basically trying to visualize what's actually going on and trying to find an approximation to more complex functions. It kind of reminds me a bit of what is it? Trying to remember. This was a really long time ago that I took any of this stuff, but it kind of reminds me of how. So you have a function and you're trying to approximate the value of that function just by, arbitrarily doing smaller operations. It's kind of like a Fourier transform to some extent, although there you're using sinusoids. I don't remember. Like harmonics, you know how you add up harmonics to get any particular shape, any arbitrary shape. But they're the base unit, like the actual building block is not a straight line or a linear operation, but it's actually a sinusoid. So a sine x. So yeah, that's what I thought. I'm trying to think of it like an easier example, but like conceptually it does make sense. It's kind of like an image, right? An image is actually analog, right? You can't you can't really express an image in a digital form, but the way they do that is through pixels. Pixels are just an approximation. So you take this arbitrary image, you cut it up into really, really tiny pieces, and then you give each of those pieces values, and that's your pixel value. But in reality, it was a continuous image, like it's an analog image, right? So yeah, that's a kind of equivalent.
You basically will find that it's going to be 5 points below. Right? It's going to be a little for loop because t equals x at weight matrix 1, t2 equals max of t, 0. Stick that in a for loop that goes through which weight matrix, and at the end calculate my loss function. And of course we're not going to calculate gradients ourselves because PyTorch does that for us. And that's about it. So okay, question.
This question about tokenization. I'm curious about how tokenizing words works when they depend on each other, such as San Francisco.
Yeah. Okay. Okay. Tokenization. How do you tokenize something like San Francisco? San Francisco contains 2 tokens, San Francisco. That's it. That's how you tokenize San Francisco. The question may be coming from people who have done like traditional NLP. Often need to kind of use these things called n-grams. And n-grams are kind of this idea of like a lot of NLP in the old days was all built up of linear models, where you basically counted how many times particular strings of text appeared. Like the phrase San Francisco, that would be a bigram, or an n-gram with n-2. The cool thing is that with deep learning, we don't have to worry about that. Like with many things, a lot of complex feature engineering disappears when you do deep learning. So with deep learning, each token is literally just a word, or in the case that the word really consists of 2 words, like your, is split into 2 words. And then what we're going to do is we're going to then let the deep learning model figure out how best to combine words together. Now when we say like let the deep learning model figure it out, of course what we really mean is find the weight matrices using gradient descent that give the right answer. There's not really much more to it than that. Again, there's minor tweaks, right? In the second half of the course we're going to be learning about the particular tweak for image models, which is using convolution, that is CNN. The language, there's a particular tweak we do called using recurrent models, or an RNN. They're very minor tweaks on what we just described. But basically it turns out with an RNN that it can learn that San plus Francisco has a different meaning when those 2 things are together.
Some satellite images have 4 channels. How can we deal with data that has 4 channels or 2 channels when using pre-trained models?
Yeah, that's a good question. I think that's something that we're going to try and incorporate into fast AI. So hopefully by the time you watch this video, it will be easier for us to do this. But the basic idea is a pre-trained ImageNet model expects red, green, and blue pixels. So if you've only got 2 channels, there's a few things you can do, but basically you want to create a third channel. And so you can create the third channel as either being all zeros, or it could be the average of the other 2 channels. And so you can just use normal PyTorch arithmetic to create that third channel. You can either do that ahead of time in a little loop and save your 3-channel versions, or you can create a custom dataset class that does that on demand. For 4-channel, you probably don't want to get rid of the 4th channel. So instead what you have to do is to actually modify the model itself. So to know how to do that, we'll only know how to do that in a couple more lessons time. But basically the idea is that the initial weight matrix, weight matrix is really the wrong term. They're not weight matrices, they're weight tensors. So you can have more than just 2 dimensions. So that initial weight matrix in the neural net, it's actually a tensor, and one of its axes is going to have 3 slices in it. So you would just have to change that to add an extra slice, which I would generally just initialize to 0 or to some random numbers. So that's the short version. But really, to understand exactly what I meant by that, we're going to need a couple more lessons. Okay, so wrapping up, what have we looked at today? Basically, we started out by saying, hey, it's really easy now to create web apps. We've got starter kits for you that show you how to create web apps, and people have created some really cool web apps using what we've learned so far, which is single label classification. But the cool thing is, the exact same steps we use to do single label classification, you can also do to do multi-label classification, such as in the planet, or you could use to do segmentation, or you could use to do any kind of image regression, or you can only if you try this yet, you can do for NLP classification and a lot more. So, and in each case, all we're actually doing is we're doing gradient descent on not just 2 parameters, but on maybe 100 million parameters, but still just plain gradient descent, along with a nonlinearity, which is normally this one, which it turns out, the universal approximation theorem tells us, lets us arbitrarily accurately approximate any given function, including functions such as converting a spoken waveform into the thing the person was saying, or converting a sentence in Japanese to a sentence in English, or converting a picture of a dog into the word dog. These are all mathematical functions that we can learn using this approach. So this week, see if you can come up with an interesting idea of a problem that you would like to solve, which is either multi-level classification, or image regression, or image segmentation, something like that, and see if you can try to solve that problem. You will probably find the hardest part of solving that problem is coming up creating a data bunch, and so then you'll need to dig into the Gradable API to try to figure out how to create the data bunch from the data you have. And with some practice, you will start to get pretty good at that. It's not a huge API, there's a small number of pieces, it's also very easy to add your own. But for now, ask on the forum if you try something and you get stuck. Okay, great. So next week, we're going to come back and we're going to look at some more NLP. We're going to learn some more about some details about how we actually train with SGD quickly. We're going to learn about things like Atom and RMS prop and so forth. And hopefully, we're also going to show off lots of really cool web apps and models that you've all built during the week. So I'll see you then. Thanks.
Cool. So that's a wrap. That was a very, very interesting video. It was one of the longer videos, so it's actually 2 hours long. But yeah, I found that very interesting. And yeah, I do think that we do need more practice. What I want to do is I'm actually going to deploy the Ryan app that I showed earlier, and I'll consolidate any feedback that we get from the forums, and then we'll share that so that everybody can benefit. But that's it. I will see you in the next video. Adios, people, and goodbye.